Hello everyone, my name is Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on equilibrium, and we've made it to the second objective, which is titled gas phase. In gas phase equilibrium, the equilibrium constant can be expressed in terms of the partial pressures of each gas involved in the reaction. This is represented by Kp, which provides a way to describe the equilibrium position using the pressures of the gaseous reactants and products. So for a general reaction in this form, where all of these reactants and products are in gas phase, Kp is calculated as the ratio of the partial pressures of the products to the reactants, each raised to the power of their respective coefficients from the balanced equation. And this specifically gives us this equation right here. Now, in this equation, PA, PB, PC, and PD, these represent the partial pressures of the gases A, B, C, and D. And the coefficients in lowercase letters a, b, c, and d, they reflect the number of moles of each species in the balanced chemical equation. This formula, it provides a straightforward way to quantify the equilibrium state of a gas phase reaction using pressure values. Now, it's also important to understand the relationship between Kp and Kc, where Kc is the equilibrium constant expressed in terms of concentration. Now, the connection between these two constants is governed by the ideal gas law, and it's represented by this equation right here. This equation says that Kp is equal to Kc multiplied by RT raised to the change in the number of moles. So R here is the ideal gas constant, T is the temperature in Kelvin, delta N represents the change in the number of moles of gas. And this is calculated as the difference between the total moles of gaseous products and reactants. This equation highlights how the equilibrium constants Kp and Kc are related through temperature and changes in the number of moles of gases. Understanding this relationship allows us to switch between Kp and Kc depending on the information available. So for example, if we know the concentrations of reactants and products, we use Kc. If we have their partial pressures, we use Kp. In addition, when the change in the number of moles is equal to 0, meaning there is no net change in the number of gas molecules during the reaction, Kp and Kc will have the same numerical value, emphasizing the role of mole changes in determining their relationship. Now, this connection between Kp and Kc is fundamental in solving equilibrium problems involving gases because it enables us to utilize whichever form of the equilibrium constant is most convenient based on the given data. And understanding these concepts is really important for analyzing and for predicting the behavior of gas phase reactions under different conditions. With that, let's go ahead and tackle a practice problem together. This problem says the vapor pressure of water at 35 degrees Celsius is 42.2 torr. Determine the values of Kp and Kc for the following equilibrium at 35 degrees Celsius. And here we see our equilibrium reaction between liquid water and water vapor. Now, something to keep in mind when you're writing your equilibrium constant expressions, you do not include liquids or solids. We mentioned this in the first part, but I want to reiterate it here because it's going to be really important for this reaction. Notice that the reactant is liquid water. We do not include liquids in our equilibrium constant expression. So the Kp equation for this equilibrium is going to be the partial pressure of water vapor. And this is specifically going to be in units of atmosphere. Now that's the second important point I want to make here for Kp, for gas phase equilibrium. Kp values, they're determined from the partial pressures of gases expressed in units of atmosphere. So we have to convert what we're given in torr to atmosphere. And that is going to give us our Kp value because Kp is only equal to the partial pressure of water vapor in this problem for this equilibrium. Now, this is an easy conversion because we know that 760 torr is equal to 1 atmosphere, so we can use that conversion. 42.2 torr multiplied by 1 atmosphere over 760 torr. You notice that these units cancel out, and our final answer is going to have units of atmosphere, and this is going to give us 0.055 atmosphere. Now, here, this is our Kp value. All right, but remember something else here that's really important. We do not write the unit. All equilibrium constants are unitless. So yes, we converted this to atmosphere because Kp values are determined from the partial pressures of gases expressed specifically in units of atmosphere, but our equilibrium constant itself is unitless. So specifically, Kp is going to be equal to 0.055. Wonderful. Now that we've determined Kp, we can calculate Kc from our relationship between those two equilibrium constants. Kp is equal to Kc multiplied by RT raised to the power of delta N, where delta N is the change in the number of moles of gas in the forward reaction. I want to reiterate this. This is really important. Delta N is the number of moles of gas that has changed, all right? Change in the number of moles of gas. So that means if your equilibrium has a liquid or solid, you do not include it in the equilibrium constant expression, and you do not include it when you're calculating delta N. So here, for this balanced equilibrium equation, there is 1 mole of water in the gas phase on the product side and 0 moles of gas on the reactant side. So our change in N, our change in the number of moles of gas is going to be the number of moles of gas you have on the product side, which is 1, minus the number of moles of gas you have on the reactant side, which is equal to 0, because all we have on the reactant side is liquid water. We do not include liquids. So delta N is equal to 1. Now, the other thing we need to figure out is our temperature, right? This is a variable that's included in this expression. Delta T is equal to 35 degrees Celsius, but we want this in units of Kelvin. So we're going to add 273 to that value to get approximately 308 Kelvin. So now we have our delta N, we have our temperature. Remember, R is our ideal gas constant. I can go ahead and write that value down for us. And now we have everything we need to use this equation to obtain Kc. Of course, let's go ahead and rearrange this so we can isolate Kc. This is going to be equal to Kp divided by RT raised to delta N. Delta N is just equal to 1. Fantastic. So this is our equation. We can go ahead and plug in our values. Kp is 0.055. Then in the denominator, we have R, 0.08206, and our temperature is 308 Kelvin. And if we plug this into an equation, we're going to get that Kc is equal to 2.2 times 10 to the negative 3. So there we have it. We figured out our Kp. It's equal to 0.055. And our Kc is equal to 2.2 times 10 to the negative 3. And with that, we've solved this problem. And we can go ahead and move into our third objective. The third objective discusses Le Chatelier's principle. This principle states that if a stress is applied to a system in equilibrium, the system will adjust to counteract the stress and reestablish equilibrium. And this principle, it can be applied to changes in concentration, changes in temperature, and changes in pressure. Now, what you see here is a summary of what happens when you change the concentration, when you change the temperature, and when you change the pressure. We'll come back to it in a little bit, but first I want to scroll to this next page and I want to consider every scenario and work through what happens when we alter these variables. Let's start off with concentration. What happens if we add reactant? If reactants are added, the system is going to shift in the forward direction to produce more products and reestablish equilibrium. What about if we remove products? When products are removed, the system will shift in the forward direction as well to produce more product to compensate for the fact that we've removed some product. So whether we're adding reactant or removing product, our reaction is going to move in the forward direction, and we are going to favor the production of more products. Now, what about if we go ahead and add products? What happens if we add product? When products are added, the system's going to shift in the reverse direction to produce more reactants and reestablish equilibrium. What about if reactants are removed? If reactants are removed, the system will shift in the reverse direction as well to produce more reactants and again, compensate for the fact that we have removed reactant. Now, in summary there, whether we add product or remove reactants, the system's going to shift in the reverse direction and we're going to favor the production of reactants. So that's what happens when we play around with concentrations. What about temperature? Now, changes in temperature, they affect the equilibrium constant itself because temperature is related to the reaction's enthalpy change. And that's going to be really important to remember when you are manipulating temperature. What happens as a result of increase or decrease in temperature is based off of whether you're dealing with an endothermic or an exothermic reaction. Now, if you're dealing with an endothermic reaction, you want to consider that delta H for an endothermic reaction is going to be greater than 0. And heat is thought of as a reactant. Heat can be considered a reactant in endothermic reactions because heat is absorbed in these reactions. So keeping that in mind, what happens if we increase temperature in an endothermic reaction? If we increase temperature in an endothermic reaction, we're adding heat, which shifts the equilibrium to the right, favoring the formation of products. Let me repeat this. For an endothermic reaction, heat is a reactant. If you increase temperature, you're essentially adding in more heat. You're adding in more reactant. What happens when you add more reactant? The reaction shifts in the forward direction, favoring the formation of product. So for this, we favor the production of product. Okay, what about if we decrease temperature for an endothermic reaction? If we decrease temperature for an endothermic reaction, we're essentially removing heat. If you remove heat, your reaction is going to shift to the left, favoring the formation of reactants to compensate for the fact that you are so-called removing heat, which is a reactant. So when you decrease temperature in an endothermic reaction, you favor the formation of reactants. All right, so that's for endothermic reactions. What about for exothermic reactions? In exothermic reactions, delta H is less than 0. And in these reactions, heat is released. So heat can be considered a product. So then what happens if we increase temperature in an exothermic reaction? Essentially, that means we're adding in product. We're adding in heat, which is going to shift the equilibrium to the left, favoring the formation of reactants to reestablish equilibrium. So if you increase temperature for an exothermic reaction, you're going to favor the formation of reactants. If you decrease temperature in an exothermic reaction, you're essentially removing heat, you're removing product. So your equilibrium is going to shift to the right, favoring the formation of products. So that's what happens when you play around with temperature for endothermic versus exothermic reactions. Now, finally, let's discuss pressure. What happens if we increase pressure? When you increase pressure, the system is going to shift in the direction that produces fewer moles of gas. And it does this because that results in a decrease in the pressure, and that reestablishes the equilibrium. Let me repeat that one more time. Increasing the pressure, this is going to shift your system in the direction that produces fewer moles of gas. What about decreasing pressure? When you decrease pressure, the system will shift in the direction that produces more moles of gas, because this is going to increase pressure to compensate for the fact that you decreased the pressure. Okay, one more time. What happens when you decrease pressure? The system will shift in the direction that produces more moles of gas so that it can increase the pressure and reestablish equilibrium. Now, here's an important note in regards to pressure. All right? Do not confuse them. They can be easily confused. And also, you can be provided the same kind of information in regards to volume, because pressure and volume are related. Now, in regards to that, these changes are then only applicable to reactions involving gases. Solids and liquids are essentially incompressible, so their concentrations do not change with pressure or volume changes. So there you have it. We've discussed changes in concentration, changes in temperature, and changes in pressure. Now, one more note. Adding a non-participating or inert substance to a system at equilibrium, this will not affect the equilibrium position. So to summarize, let's go back to this table and quickly discuss what happens when we change concentration. The system is going to shift to counteract the change, moving away from added species or towards removed species. What about for temperature changes? For endothermic reactions, increasing temperature favors products while decreasing temperature favors reactants. For exothermic reactions, increasing temperature favors reactants while decreasing temperature favors products. And then finally, for pressure, the system shifts to produce fewer moles of gas when pressure is increased or volume is decreased, and more moles of gas when pressure decreases or volume increases. Keeping that in mind, let's go ahead and tackle a practice problem together. This problem says, consider the Haber process for the synthesis of ammonia. And we're given this reaction. 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to give us 2 moles of ammonia. In addition, we're given the change in enthalpy. It is equal to negative 91.8 kilojoules. This value is less than 0, so that tells us this reaction is exothermic. We need to figure out which would increase the equilibrium yield of ammonia. What kind of change is going to shift the equilibrium to the right, favoring the formation of products? So let's work through each of these options. A says increasing the total pressure by compressing the system. Now, compressing a gas phase reaction is going to result in an increase in the total pressure of the system. The system can counter this increase in pressure by shifting to the side with fewer moles of gas. Now, looking at our reaction, looking at our balanced equation, we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. Therefore, the system is going to respond by shifting to the right and thus increasing the equilibrium yield of ammonia. So option A does in fact increase the formation of ammonia. What about B, the addition of a catalyst? Now I included this because I wanted to discuss catalysts and how they affect equilibrium. Although a catalyst enables a system to reach equilibrium faster, it will not affect the equilibrium position. So in fact, the addition of a catalyst would not increase the equilibrium yield of ammonia. Then finally, answer choice C says increasing temperature. Now, what we have here is an exothermic reaction. And we said for exothermic reactions, we can consider heat as a product. If we're increasing temperature, we're essentially adding heat into the system, which means we're adding product. If we're adding product, our system's going to shift to the left and favor the formation of reactants to reestablish equilibrium. So that would mean that by increasing temperature, we're going to shift the equilibrium to the left, favoring the formation of reactants, not products. So this change would actually lower the equilibrium yield of ammonia, which is not what this problem is asking. So the only option that's correct here is answer choice A. The only thing that's going to increase the equilibrium yield of ammonia from the 3 choices we're given is A, increasing the total pressure by compressing the system. And with that, we can go ahead and move into our last and final objective titled Kinetic and Thermodynamic Control. In chemical reactions, products can often be classified as either kinetic or thermodynamic. Understanding the differences between these products and the conditions that favor their formation is really important in predicting and in controlling the outcomes of reactions. Let's start with discussing the kinetic product. The kinetic product is the product that forms the fastest. It is favored under conditions that limit the reaction's ability to reach equilibrium. What are those conditions? Lower temperatures and shorter reaction times favor the kinetic product. And these conditions favor the formation of the kinetic product because it forms through a pathway with a lower activation energy, even though it might not be the most stable product. What about the thermodynamic product? This is the most stable product. It is favored under conditions that allow the reaction to reach equilibrium. What are those conditions? Higher temperatures and longer reaction times. With sufficient heat, the reactants can overcome the high activation energy barrier to form the thermodynamic product, which exists at a lower overall energy state and is thus more stable. Now, a reaction coordinate diagram, like you see here, this is a graphical representation that shows the energy of a system as a reaction progresses from reactants to products. The height of the hills or peaks that you see on this diagram represent the activation energy that's required to reach the transition state from the reactants or from the products. In terms of the kinetic pathway versus a thermodynamic pathway, well, the kinetic pathway is often associated with the lower activation energy peak on the diagram, leading to the formation of the kinetic product. Again, this is because the kinetic product forms faster due to the lower energy barrier that needs to be overcome. On the other hand, the thermodynamic pathway is associated with the product that exists at the lowest overall energy, despite potentially having a higher activation energy peak on the diagram. This is the thermodynamic product, which is more stable. Now, in biochemical systems, the principles of kinetic and thermodynamic control are really relevant. Many biochemical reactions are regulated to favor either the kinetic or the thermodynamic product based on the organism's need. So for instance, metabolic reactions are going to often involve ATP. This is a high energy molecule. The breakdown of ATP is thermodynamically favorable process, but it's controlled kinetically by enzymes in the body to ensure that it only happens when needed. In enzyme activity, factors such as temperature and solvents can alter the balance between kinetics and thermodynamics. So for example, higher temperatures can provide the necessary activation energy to overcome barriers and reach a more stable thermodynamic product. However, enzymes being proteins can denature at high temperatures, thereby favoring the kinetic product. And so, in summary, whether a reaction follows a kinetic or thermodynamic pathway really depends on the reaction conditions, and understanding this is going to provide us insight into the control and regulation of biochemical reactions. And with that, we've completed our chapter on equilibrium. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.